All right, this is chapter 3, section 4, rates of change. Instantaneous rate of change we learned the other day is the derivative. So our derivative definition, f prime of a equals limit as h approaches 0 of f of a plus h minus f of a over h. So really what it comes down to is to find the instantaneous rate of change at a point A. We simply need to find the derivative and plug in a. For example, if I want to find the rate of change of the volume of a cube with respect to its edge E, say I have B of E equals E cubed, rate of change would be V prime of E equals 3E squared. If I throw in that I want to find the rate of change at a specific edge length, I could plug in 5 for E, like V prime of 5, so when the edge is 5, the volume is changing at a rate of 3, 5 squared, or 75 cubic inches per inch that I changed the edge. So something along those lines. But the rate of change, instantaneous rate of change, is the derivative. So that's our big discovery. Instantaneous velocity is a connection here, connection piece to physics. Our instantaneous velocity, v of t, is what we use for velocity, is equal to the derivative of s with respect to t, where s is the position function. And that's defined to be the limit as delta t. Delta t represents a very small change in time. So delta t, so t plus delta t is kind of like our x plus h, where h represented a very small, relatively small value. So it's, once again, the difference quotient, just popping in there t's and delta t's instead of x's and h's. But v of t, velocity, is the derivative of the position function. And acceleration happens to be the derivative of the velocity function, or the second derivative of the position function. If we're given that h of t is the quadratic function, h naught plus v naught of t minus 1/2 g of t squared, so it might take the form of this. There's a rock being launched or slung into the air, but the height of a rock is given by h equals 3. 3 is the h naught, plus 135t. 135 is the initial velocity. We call that v naught. Minus 16t squared. We get 16t squared by taking half of the gravity constant, 32 feet per second squared, and then t squared. So find the velocity and acceleration. So what we're going to do is just find h prime here, which is going to give me my velocity function. So, and then h double prime will give me my acceleration function. So velocity of t is equal to h prime of t, which equals 135 plus, or minus, I should say minus. So plus a negative 32t. So we'll put our negative 32t in there. So it should be a minus 32t. And then acceleration with respect to t is the second derivative of this guy. It's h double prime of t, which just equals the constant negative 32. So we're seeing this constant acceleration due to gravity popping out of this quadratic equation, which we would expect just on our understanding of the power rule, how it works. So given a position function or a height function that's a quadratic, the velocity, instantaneous velocity at a point, is given by this linear function, 135 minus 32t. So we've got v of 3, we're going to plug in 3 to that function, gives us 135 minus 32 times 3. 135 minus 96 is 39 feet per second. And when t equals 6 seconds, v of 6, is equal to 135 minus 32 times 6, and we get negative 57 feet per second, which just indicates a change in direction. It's coming back down, in other words. Negative 57, you can have a negative velocity. Now, acceleration is the same for both of these. It's a constant. So a of t is equal to negative 32 feet per second. It doesn't matter if it's at 3 seconds or 6 seconds. The acceleration due to gravity remains the same, which makes sense with what we understand in terms of the physics of what's going on here. All right, so we've got position function. Derivative of that is velocity function, instantaneous velocity. Derivative of the velocity function then is acceleration. So suppose, this particle motion we're going to summarize here, but suppose we have s of t as our position function on a closed interval a to b. Position would simply be s of some value t here. So position is just s of t. You're usually given a function. Displacement is final position minus initial position. How would you find the total distance, or how would it differ from displacement? Displacement, like velocity, could be negative. If I wanted total distance, it would be summing up the absolute values of these different displacements that I might have over different intervals. I have to be careful when I do that. We're going to talk more about that next semester, but it's a summation of the absolute values of these velocities multiplied by that time interval over which you're at that particular velocity. So you could figure out total distance. In some cases, it wouldn't be too bad. Rest of this here, we've got how does final position relate to displacement? Final position would be equal to, if you think of displacement as final position, we'll abbreviate it here, minus initial position, then final position would just be moving this over here, doing a little algebra, would be initial position plus displacement. We're going to look at that as well in more detail next semester. That's something that shows up frequently on the AP exam, is finding the final position of some particle in motion. Average velocity, just to review, is, in this case, if s of t is our function and we're on the interval from a to b, it would be our y2 minus y1 over x2 minus x1. And in this case, it would specifically be s of b minus s of a over b minus a. And then there's one other definition we have not yet touched on here. We've looked at velocity, or position, velocity, acceleration, displacement, reviewed average velocity. There's one more in here that we need to talk about, and that is speed here. So, instantaneous velocity we know to be, let's put it in the same slot here, v of t, which equals s prime of t in terms of the position function. And then speed is the absolute value of v of t, or absolute value of the derivative of position. So there's a relationship between speed and instantaneous velocity, and the relationship is it's the absolute value. Velocity can be negative. It just denotes a change in direction, which we're going to see on our little activity at the end of class. as we look at a velocity graph. And then average velocity is the velocity over an interval. Displacement can be negative. Total distance traveled will not be. It's sum of the absolute values of the velocities over their different time intervals. All right, here's a velocity graph. So the question is, can there be negative velocity? You mentioned that before. Yes, we saw it on one of our examples. It just denotes a change in direction. We can see it in this picture right here. We see a change in velocity. We see it at x equals 5 or t equals 5 and also at t equals 7. It changes from positive velocity to negative velocity at t equals 5 and then from negative to positive at t or x equals 7. What would negative velocity indicate on a graph? It just means going in the opposite direction from which you started. How does negative acceleration affect the velocity? Well, if you think about it, when I'm shooting something up into the air at a certain initial velocity, it can't help but slow down because of the opposing force of the constant of gravity. So the constant of gravity is negative, 32 feet per second squared. I'm shooting something up at a positive feet per second, so that negative 32 feet per second squared is slowing it down and eventually going to turn it around and it's going to start falling back towards Earth. So some questions here on this graph. You just kind of sketch this graph. I want to be able to answer a few questions here about the graph. Remember, this is velocity versus time, so it's like a derivative graph that we looked at before. Okay, velocity versus time. So we've got basically a derivative graph going on here. So when does the body reverse direction? That is at t equals 5 and t equals 7 seconds. When is the body moving at a constant rate? We see that happening only from the interval between 2 and 4 in interval notation, 2 to 4 seconds. It's moving at a constant of 2, and then the units are feet per second, or in our activity we're going to do it's feet per minute in our hiker activity. And if we graph the speed on the same graph using a different pen, we're going to do that right now. Different color pen, we'll use the blue. It's the absolute value of this graph. So anything that's below the x-axis is going to get reflected over the x-axis and up. So there in blue is the speed graph. And if I wanted to, in another color, do a graph of the acceleration. Remember now, this is velocity. Acceleration is derivative of velocity. So if I calculate the acceleration of this first line segment right here, it's the slope of that line. So the slope of that line is 1. So I have from 0 to 2, my acceleration graph in green here would have a slope of 1. So I'm graphing the slopes of these 1, 2, 3, 4 different line segments. So the next one from 2 to 4 has a slope of 0. So I have an open circle at 2. It would go staying at 0, go to 4. And the next one has a negative slope. It's a slope of negative 2. So from 4 to 6, my graph would be a horizontal line at negative 2, representing the slope. So once again, this is my graph now, A of t versus time. And the final one has a slope of 2. So I jump back up here. I have a slope of 2 from 6 to 8 seconds. And that's it. So what class was asked to do is to write a story about a hiker that relates to the graph. Be sure to address the hiker's direction, velocity, acceleration over each time interval, and the reason why. This is the graph that we're looking at. So in class we came up with some very creative stories in terms of what could have happened to the hiker, but we've got some key features here. From 0 to 2 minutes, the hikers may be packing their bag or getting ready, eating a sandwich, or different things going on, tying their shoe, things like that. From 2 to 4 seconds, the hiker is accelerating up to and then holding at a speed of 200 feet per minute. That's the blue line segment there. And then the hiker at some point speeds up, accelerates up to 400 feet per minute fairly quickly, and then starts to slow down all the way down to 0 feet per minute, and then completely changes direction at that 12-minute mark and accelerates in the opposite direction until hitting a speed of 400 feet per minute and then comes to an abrupt stop. That's right around the 17 or so minute point there. So we wrote little stories that could have happened to some hiker that would correspond to this graph. So have some fun with that. Maybe think about what that might look like. Your task is to be able to take this, basically this derivative graph, this velocity graph, like the derivative of the position function, and maybe talk about what might have happened in real life, in real scenario in terms of their position. And then also think about the derivative of this graph, which is acceleration, which represents the slopes of the tangent lines to these curves at different segments here, and those you'll see in different colors here. So that's it, I think.